is Opubo. In this channel, I present various ideas and designs of technologies, mostly from the Technology Bank of Enhanced Knowledge LLC. This presentation focuses on algae cultivation process bioreactor technology, which is specifically developed for the large-scale production of algae, or the everywhere common and offensive pond scum, for the production of nutraceuticals as omega-3, a substitute for fish oil, production of biopharmaceuticals such as astaxanthin, which is the red colorant on the red snapper, which has been determined capable of prolonging mental acuity and resetting stem cell ages to younger years, production of biofertilizers, which are mostly in the amino acids or steroid chemical compound state that accelerate and enable plant bypass the stage of conversion of food into the compound states and therefore cause plant rapid assimilation and hence rapid growth, and the production of biofuels such as bioethanol, biobutanol, and biodiesel, all produced from algal lipids and carbohydrates that enable greenhouse gases recycling in the ecosystem and so mitigating global warming. Digressing for a moment, however, if you have not as yet subscribed to the channel, by simply clicking on the subscribe button below, I implore you to do. Please click the subscribe button now. The subscription would cause the system to keep you informed by notification of the next presentation the moment one is published. Now, back to the presentation. The reality is that currently, the production or cultivation of algae on large scale for industrial operations is scant and not undertaken by many. Most of the production scale cultivations with horizontal tubular reactor, vertical tubular bioreactor, channel ponds, or photobioreactors are not very cost effective for industrial operations. So the use of algal biologics are for special purpose high-end value products. Yet algae are the most effective raw materials for the production of just about all the needs of mankind. Therefore, developing a cost-effective process is essential. By and large, it is an expensive process, of course, unless well planned for before inception. Preferably, it is best to shift the investment cost into initial capital investment instead of heaping up in the operating expenses, which has been responsible for the lack of performance. All of that effort, however, starts with the availability of a well-designed photobiological reactor. The object of this presentation is precisely one such well-designed algae cultivation process photobiological reactor technology. Algae cultivation process bioreactor. Though supporting standalone operations, the use is not just as standalone primarily, but truly as a production process technology. The preferred deployment of the bioreactor technology is as bioreactor in biological process technology. Hence the moniker qualifications, process bioreactor. The process bioreactor technology consists primarily of the photobioreactor process equipment, 2 appliances, the controller appliance with algorithm for controlling the bioreactor performance, and the database appliance for the performance data storage, and 2 thin clients, the operating conditions setter thin client, also known as the operator thin client, and the controller conditions setter thin client, also known as the controller thin client. Both thin clients are supported by the controller appliance. Technically, the system is a simple distributed computing system with 2 thin client front end. Distributed computing system design is critical because every adjustment of the controller is automatically logged in the database for later review and analysis and decision making. Besides, this infrastructure empowers the controller appliance as the exclusive point of communication and exchange of data with the bioreactor, and therefore drastically reduces the degrees of freedom of failure, thereby minimizing failure. Moreover, This infrastructure allows for the implementation of several redundancies and failovers of the controller, and therefore further prevents potential interruptions. Now, when deployed within a process technology, the operator thin client is stationed at the location of the bioreactor for the use by the bioreactor operator. The appliances are packaged into multi-computer distributed computing system, and with a central controller view system as the first tier, and into which is embedded the controller thin clients. However, for such purposes, the thin clients are much wider. Now, regarding the specifics of the technology, the bioreactor process equipment design is a good start point. The reactor equipment by design is basically a process tank, and it's like any standard cylindrical tank, but covered at both ends with wide diameter bowl-shaped caps, and of course there are no side view ports. On the body of the reactor equipment is affixed an electrical panel. At the top cap are affixed a variety of instruments: thermometer, barometer, stirrer, viewport, light pot tube, and one feed port for feed mixture of fertilizer plus nutrients, densitometer or particle counter, acidometer, pH meter, and effluent gas outlet. At the bottom cap is an off-center feed port for carbon dioxide and a central effluent port for acquisition of the product at harvesting. There are, of course, auxiliary devices and equipment that serve different purposes. For instance, you have a cooler condenser, a light intensity controller, a feed flow rate controller, and a feed temperature controller. Of course, all the wires and cables connected to each of these instruments and devices and equipment of the top and bottom caps are wrapped into a bundle and put into the electrical panel, from inside which the panel additional wires and bundles are added on and channeled out to the controller appliance for data input and output. Of course, the design details of the interior is proprietary and accordingly being omitted. Now, relative to most other bioreactors, this design is for large-scale cultivation of algae and suited for that deployment for several reasons. First, it maintains tight control of the air bubble size to allow for surface volume ratio comparable with raceway channel ponds, effectively capturing the primary functionality of raceway pond control of absorption surface area to volume ratio setting. The mixing of the bioreactor is consistent with the design specifications and therefore maintains stable state of mixedness. The reaction medium being closed off from the atmosphere ensures no contamination of the suspension or culture. The continuous supply of premixed feed, ensuring constancy of feed and near uniform distribution, assures near constant reaction time or even residence time when deployed as a continuous flow stir tank reactor. The irradiation of the reaction mixture being supplied under tightly controlled conditions results in constancy of intensity of the light irradiation on algae suspension, assuring virtually constant reaction time. Further, the irradiation of the algae suspension being performed only with sunlight ensures the irradiation enforces strict natural day and night status of the existence of the algae. That brings us next to the specifics of the operator thin client used for setting the operator conditions of the bioreactor. This is the specific thin client which the operator uses to set the operating conditions of the bioreactor. The operator thin client is a bare-bone handheld computer with data intake interface as the large black screen LED for display in the center, and with the shift sign-in controls to the right and the operating condition setup buttons to the left. The operator thin client also has a messaging app by which the operator sends messages to central control management or any other designate for alert. The messaging app has direct communication link with control room and also used by the bioreactor operator to write reports of state of operations, which can also be filed through the controller theme client in the database. Sign in by operation for shift start requires input of ID, password, and fingerprint biometric. All input settings are channeled through the controller, which performs preset validation with feed-forward analysis prior. Although the setup buttons shown on the left panel surface are not exhaustive, all properties setup buttons are placed on the left side panel surface. The controller theme client, which also communicates with the controller appliance, is a more robust handheld computer with the data intake and display interface as a large black screen LED in the center. And the controller theme client is in fact a complete touch screen, and so only has the sign-in fingerprint biometric on the left-hand panel surface. After the initial sign-in, the touch screen then requests other credentials through the touch screen before letting access to the controller appliance. This theme client is used to select at configuration the algae growth custom control algorithm for the specific production need and the specific algae. The controller theme client actually is used to set the parameters of the control algorithm and to also observe the state of the bioreactor and of operating conditions set for the operations. Algae-specific controller algorithm, custom software, high productivity, being of superior advantages are all features relative to others. At operation of the bioreactor, gas stream either of air or of a mix of carbon dioxide and oxygen is pumped into the bioreactor gas feed port at the bottom from a retrofit gas reservoir, and to prevent contamination, the gas stream is passed through an absorbent filter that cleans out even micron particles. Similarly, a feed stream of nutrients and fertilizers, preferably biofertilizers, mixed in water as suspension is pumped into the bioreactor also continuously, and distilled water is used to premix the fertilizer and nutrients, and stream sanitized before being fed into the bioreactor. The motor of the stirrer is switched on to have the stirrer started, and light radiation switched on as well, with light being transmitted from solar collectors functioning collectively as the light source. Algae species is then charged into the bioreactor. The gas effluent line is connected to the cooler condenser and the return feed back to the feed line and fed directly into the bioreactor. The water is refiltered and post-mix feed sanitized before entering the bioreactor. The effluent gas of the cooler condenser is then handled with respect to the context of industrial operations. The deployment for industrial operations also has attendant benefits, and there are two types of industrial operations. The non-biofuel driven large-scale production of algae and the biofuel objective large-scale production of algae for substitute of fossil fuels. The biofuel driven production must necessarily support time compression as explained in the presentation high productivity algae raceway channel pond. Therefore, the bioreactor designed for use in biofuel production must support time compression. The differences between the two are as follows, starting off with the non-biofuel driven production or the regular production operations. In this case, the gas reservoir can be simply the atmosphere or a gas tank of carbon dioxide source. Operations from which more than lipids and starch are extracted from the algae must have the biofertilizer and nutrients continuously freshly supplied. Now, for the biofuel-driven industrial production, a typical biofuel process plant is anticipated to include about, on the average, 200 bioreactors per plant. In that particular case, or for building such process, the appliances are organized as with standard multi-computer system. But most importantly, given that the operation designed for use in biofuel production must support time compression, it follows that gas source be of a negative emission process carbon dioxide source. Also, the effluent gas of the cooler condenser must, for efficiency, be returned to the negative emission process for real extraction of the excess carbon dioxide. Moreover, from lipids and starch extraction processes, the post-extraction waste must be recycled to a biofertilizer and nutrients process plant in order to conserve phosphorus for life. Because this bioreactor supports a very narrow spread of the residence time distribution, even though binomial, at mean plus minus 1 standard deviation, and the production demands uninterrupted continuous production, the bioreactor must be deployed in a bioreactor system, which is a set of this bioreactor interconnected into a chain continuous flow stir tank reactor. Despite the large number of bioreactors requirement to support biofuel process plants, effective land use can still be managed to limit the sprawling of need for land as with raceway channel ponds. This result is achieved by build-up with a hive nesting structure. A cube or a rhomboid structure is built, the bioreactor installed within, while allowing for ambulatory spacing. This structure forms a hive and the target biomass, and on the target biomass, the hive goes into build-out horizontally along width and length, and then vertically high, and then high productivity is achieved. As the presentation comes to a close, it is worth noting that this bioreactor, being based on process equipment, brings several advantages to the large-scale commercial production of algae, including the rapid construction from numerous available used process equipment, the reuse of process equipment, and therefore a minimalist attitude to natural resources management. The process equipment is off the shelf and already pre-developed, so it's easy to even buy a new one. And then there's the plentiful experience of plant process equipment operators who would be ready to perform the operations. If you have enjoyed this presentation, then I implore you to also click the like. It makes it easier and better for me to be able to bring you more informed presentations. Thank you.